Hello everyone, welcome back to continuing lectures of computational process design. We would continue from where we have stopped since the last class. So, we were talking about optimization methods for process design, and this is the part 2 that we try to complete. How do we do the proper scheduling, how do we do the inventory management, these kind of questions we try to answer in this particular lecture. So, again if we move on, the textbook that this particular topic that we always use is Wigler, Grossman and Westerberg, Systematic Methods of Chemical Process Design. So, we will start from where we have stopped in the last class. What we were talking about, how the design, operability, process control and scheduling are related. Classical design methods tend to decouple operations and design, but there is a strong synergy between both of them. So, you can always design an equipment and you can actually smartly operate them, okay, so that even if your design is of lower capacity, your operational schedule or operational procedure, operational recipe would help you to manage with that in an optimal fashion. So, typically speaking, design and operation are not two things that to be seen separately. Ideally, one has to uh, one has to integrate them together. So, we will start with where we have stopped on operability. Operability in process design refers to the fundamental principle ensuring how process can be operated freely, efficiently and reliably. Okay. This encompasses various aspects that includes reliability, safety measures, how to maintain an equipment, how do you handle the variability in the feedstocks and so on and so forth. So, see, the operability consideration must be integrated with the initial design space, and and once you are in operation, once the equipment is in operation, and these again these operational challenges has to be taken into consideration. Also, in case of retrofitting essentially means that you actually modify the equipment over a period of time. What is the new challenges that you need to take into, that has to be taken into consideration. Now, coming to process control. Control is also very closely linked to operability, and it is essential for maintaining the desired performance in the chemical process. One cannot just say that I have designed the equipment, I have installed it, and it's no more my responsibility to get the product out of it. It should happen on its own. So, but the control and operability, when you integrate with the design, would help you to give you the synergistic approach to reach the desired product in an optimal fashion. Typically, process control may involve feedback or sometimes feed forward, wherein you try to control the temperature, pressure, flow rates and composition the variables such as the key process variables. Also, key effective control ensures system process stability, consistency and quality, and the ability to respond to changes or disturbances. This is again in connection with the operability. So, in context of process design, control strategies are tailored to specific objectives, whether it involves retrofitting or the existing system or even designing to a new one. Now, let us see what is retrofit designs. Okay. So, when you make an equipment, okay, and over a period of time, your objectives might change over time. Okay, so you may need to process certain certain feed in a larger throughput. You may have to bring down certain uh, throughput of certain feed, or the entire process technology would have changed. So, you need to integrate all of them in retrofitting. So, retrofitting involves changing the chemical process to address various objectives that includes improving the efficiency, reducing the operating cost, enhancing safety, and of course meeting the environmental regulation. And a key principle that always used in retrofitting is what is known as debottlenecking. Debottlenecking is just to avoid and identify the bottlenecks and eliminate them in the process design. This can be achieved by, again, you could upgrade the equipment, optimize the process, or modifying the process flows, so on and so forth. So, retrofitting could involve maybe redesign itself, or maybe incorporate new technologies in instrumentation and automation, uh, or something else as well. So, it is also, retrofitting is also connected to process changes. For instance, it may also include changes in the feedstock selection, process specification, process condition to align with the demands or sustainability goals. So, what is process scheduling? So, now we try to connect with the fourth term. So, we started with operability, we spoke about process control, we spoke about retrofit design, and also on process scheduling. So, the process scheduling involves, again, it is very closely linked to retrofits design. It involves planning how modified process will operate efficiently over time. Scheduling ensures the right resources, including equipment, manpower, and raw materials, such that it can be allocated in a principled fashion. Efficient scheduling would minimize downtime, maximize of course the production throughput, optimizes resources utilization, leading to cost savings and improved profitability. In context of retrofit projects, scheduling helps to plan how modification can be undertaken and how this would be implemented with minimal disruptions into the ongoing production. So, the other aspect in retrofit design and process scheduling, or even in operability and process control, scheduling would help you to organize the process. Even though your design capacity is minimal, by properly scheduling whatever operations that you want to achieve, you will be able to achieve the desired target. So, before we move on to scheduling, let's briefly speak upon batch as well as continuous process. So, there are two types of process, of course. One is in chemical engineering, one is batch and continuous process. So, what are the key differences in batch process? So, let's have the following things evaluated, how things would work in batch as well as in a continuous process. Let's consider reaction kinetics. Complex reaction kinetics and better reaction conditions often favor batch process due to better control. Batch process essentially means that you charge the reactant or the desired process input ingredients into your batch reactor. We have learned about batch reactor in the previous classes and you let the process to continue until the desired target is achieved, and you take out the product and you kind of separate them, or even do various downstream tasks that you would like to do. So, in reaction kinetics, yes, if the reaction kinetics is complex, it's better to have batch process because you have better control. And in terms of flexibility, batch process may have better flexibility because you can produce different products and composition as needed. In terms of safety, okay, hazardous reactions or toxic intermediates can be better managed in batch mode through close monitoring, because you don't have too many equipments to monitor, you have only a batch equipment you monitor. Okay, so scale. So, scale in the sense that batch process, okay, typically is cost effective for smaller scale production. So, see, if you wanted to only produce lesser amount of quantity of certain product, you don't have to create such a large scale continuous process plant. You can do it in a small scale. Yeah, but on the other way around, if you are interested in larger production scale, typically batch process are not really favored. And in terms of product quality, So due to special precise control which we can attribute to, batch process are typically suitable for high purity or specialized product. For instance, most of the drug related product, healthcare related specialized products are typically made in uh, batch processes. So, considering the fact that you have only one batch reactor and its associated ancillary equipments to deal with, batch processes are easier to start and stop because you don't have to go back and run around the entire chemical plant. Your focus typically be limited to a batch process and its ongoing and its battery limits. And equipment and infrastructure also. So see, how do you choose batch or continuous? So you need to have, so your availability of suitable equipment and infrastructure is what actually helps you to choose between batch and continuous. And energy efficiency, but continuous but if you talk about energy efficiency, continuous processes are more energy efficient under steady state condition, and but batch processes have a lower startup energy while operation. So, including in terms of overall economics, so that is what you actually play a key role in decision making when you need to choose batch or continuous process. So, the effect of scheduling would typically would be a matter when you have batch processes, because you have independent components and you are charging them in by batch, and every equipment has its role to play. Okay, then the subsequent equipment would be coming to the picture. So let's look at a small schematic as been over here. Okay, so we have a reactor wherein we mix raw material A to B and we heat them up to certain degrees centigrade for certain time. Okay. And A and B would react to form C, which we entirely transfer to a mixing tank, okay, wherein you add a solvent for a better separation. And this mixing tank, we spend for an hour in ambient temperature for separation, and the mixture is again taken back to a centrifuge, wherein the liquid A, B, D are separated, and the solid C, which is the product, which is taken out for drying and for subsequent process. Let us assume that. So, all these equipments are now operating in batch because the reactor first operates, then when the reactor operation is done, you transfer the process to the mixing tank. Once the mixing tank operation is done, you transfer them to the centrifuge, then to the tray, and finally tray dryer, and finally for other packaging and other subsequent downstream operations. So, now let us talk about where is the scope of scheduling coming into the picture. Okay. So, let us see. So, you have 4 stages here. Stage 1 is reactor, stage 2 is mixing, stage 3 is centrifuge, and 4th stage is of course the drying. So, let us say, and we have the time for each of them. First is for 4 hours, second is for 1 hour, next is for 2 hours, and the last is for 1 hour. So, now how do we integrate them? Okay. So, one first scenario is when where the transfer times are not overlapped by the production stages, they add directly into the cycle time. Cycle time is when you complete one entire cycle of the process. Okay. So, what would happen after 4 hour completed? Okay, you move from stage 1 to stage 2, then to stage 3, then stage 4. But you have to understand that in between between stages there would be some time for transfer. Ideally, if you need to account, the figure in the bottom shows that such a transfer is negligible. Okay, and the transfer time can be overlapped with processing time of the subsequent stages. So, basically the transfer from a stage 1 to stage 2 would typically happen simultaneously and by overlapping with the operation of the particular stage. By doing so, the transfer time does not would add to the cycle time because it is absorbed in the processing time. So, this is an idealized condition. You may not be able to find such a case wherein you can do a we can do a very quick transfer from a stage to its subsequent stage and move on. But typically there would be, you would identify that there would be certain transfer time that comes into the picture. So this is this particular so what we are showing is the schedule of operation, how stage 1 to stage 4 uh, and how they are scheduled. In the first case, you assume that there is a transfer time. In the second case, not. Such a graphical representation of the schedule is typically known as Gantt chart, and we know that this is a single product batch plan. In the previous example that we have seen, we are only considering for a single product. So now let's see how can you minimize the cycle time in a single product batch plan. The single cycle time is something that actually limits the operation of an equipment when repeated operation of the equipment. So let's assume that the processes are non-overlapping. Okay, essentially mean that you are doing the process sequentially. You are at stage 1, then you move to stage 2, then you move to stage 3, then you move to stage 4. Okay, once all the stages are completed, your stage 1 is reactivated for the entire for the second batch operation. So, what is cycle time? Cycle time is the time that is needed for the stage 1 operation again to come in line. Okay, so that it can be brought back to the operation, brought back to the physical operation. The total cycle time in this case would be 4 plus 1 plus 2 plus 1. This would be in this case is 8 hours, and the make span, let's say if you are considering 2 batches, make span is the time that is needed for the entire operation to complete. So in this case, the first operation would take 8 hours, second operation would again 8 hours, 8 plus 8, make span would be 16. So now what is the cycle time? So cycle time, when you see that, so cycle time is when your stage 1 here when again been reactivated after the first level of operation. So stage 1 here, so in case of non-overlapping operation, stage 1 the cycle time would be the summation of all the stage operations. So that's why it become 8. So consider the case when they operate overlapping fashion. So essentially means that after 4 hours, okay, your stage 1 equipment is now free to reuse. Okay, so essentially means that after 4 hours you can restart your stage 1 and you don't have to wait until you complete your stage 4. So you start with stage 1 again just after the first after it's complete the operation. So what you would see here that then after that time point, you see that 2 operations would be running in parallel. Okay, the batch 1 batch 2 is immediately started after 4 hours of the batch 1. Okay, batch 2 would continue into stage 2. At that time batch 1 is going on because batch 1 will take 4 hours. Then batch 2 batch 1 again moving to the stage 2. Okay, so then again to the stage, so stage 2, stage 3 and stage 4. So then immediately after that, after 4 hours, okay, you can reactivate the stage 2 of the batch 2. Okay, then stage 3 of the batch 2 and stage 4 of the batch 2. So what is that we are saying here? So your equipment's ideal time is typically now reduced. What I am trying to say here is that your batch stage 1 equipment that you used for the operation, you can quickly brought back after that stage is completed. So as a result, the cycle time would be much small. So cycle time here is 4 because your stage 1 equipment is again in operation after 4 hours. So as a result, what would happen? The total operational time for the entire 2 batches, which we call it as the make span, is also reduced. How much it will take? 4 plus 8 plus 4. It would be just 12 hours. So you can see that there is a 4-hour reduction in terms of cycle span and cycle time, and 4-hour reduction in terms of make span. So so what is, how do you compute the cycle time operation as a cycle time computation if it's an overlapping operation? So overlapping operation, it is computed as the maximum of the individual stage time. So that is only limiting factor over here. So after the maximum operation, the other one can be brought into line, while in if it's a non-overlapping operation, you have to complete the entire operation of all the stages, which is summing up to to the overall time that is needed for the entire process to complete. Okay. So, this is how you smartly start doing these things. So, by means of geometry and heuristic itself, we now find that there are ways to improve the overall production time. So, you do not have to actually increase the size of an equipment. Okay. So, you can provide them, you can actually integrate them suitably while operation, so that your operational debottlenecks can be smartly accommodated. So, now we will move on. So, what we have seen was a single product batch plan. Now, we will look for the case when you have multi products. Multi product essentially means that the production line is organized in a way that each product follows some sequence of operations or processing stuff, and maybe multiple products may be produced in parallel in different lines or different lines or lanes. So, you can see here, you can see that you have 4 such units, and there are multiple inputs that is coming in. Okay. So, you have multiple lines, and you might eventually getting out multiple outputs as well. So, you can also see a different scenario over here, wherein where 2 directions are in the forward, and one of course tend to bypass certain unit and eventually reaches the output. In the other case, one line that is moving in the reverse direction. So, typically all the job shops layout are characterized by flexible work centers or machines that can perform a variety of operations. See, none of the equipments is considered or would be considered as idle in any process plan, because we tend to reuse them smartly, so that their downtime is typically, or what we call it as downtime, slack time, okay, etc., can be reduced. Products move from one machine to another based on specific processing requirement, and there may be significant variations in the routes as well. So, you can see here in this case everything is in the forward, while in this case you say that some directions are backward, there are bypasses, recycles, and so on and so forth. So, how do we do, how do you identify schedules for mixed product campaigns? Okay. So, you have 2 products here, A and B, and both of them pass through 2 stages. This is of course an illustration, 2 product plans for geometric illustration, schematic illustration. You have both of them has to pass through 2 stages of operation. Okay, and you have first stage 1 for A has to go through 5 hours, 5 time units, for instance, let it be hours now, and stage 2 is 2 hours stage, and product B has to pass through stage 1 in 2 hours and stage 2 in 4 hours. So, this is a slightly more convoluted problem to resolve. So, the key difference here, the key difference in scheduling between single product campaign and multi product campaign is the level of complexity and the resource allocation. Typically, single product campaign is dedicated to producing one product at a time, leading to higher efficiency, and multi product campaign involve concurrent production, as in we see over here. We can just see. And that may involve more careful allocation, changeover requirement, and diversification strategies, and to balance the overall operation. So, look at 2 operational strategies, okay, wherein you only look at so here the blue color indicate the product, the A, and the orange color indicate B. Okay, you can see that stage 1 of stage 1 of A, stage 2 of A, stage 1 of A, stage 2 of A, stage 1 of A, stage 2 of A. Then you start stage 1 of B. Okay. So, stage 2 of B, stage 2 stage 1 of A, stage 2 of B, stage 1 of B, stage 2 of B, and so on and so forth. So, this is one way to organize this production problem. So, as a result, what would happen? Your equipment would be in line, will only come after 25 hours, and the make span has happened to be 29 hours. So, see, because up till here, okay, up till here each of them would be under operation, and overall time would be from here to here, which is corresponding to 29 hours. So, now look at a different strategy. Okay. So, you can see stage 1 of A, okay, stage 2 of A, just immediately after that you start producing B, okay, stage 1 of B, again stage 2 of B, just after that. So, basically it is what you call it as, this is A production followed by B production. So, overall we would make 3 batches of A and 3 batches of B. So, look at over here, this is A, B, okay, then you come back and start producing A, then you come back and you start producing B, then you come back and start producing A, then you come back and start producing B. So, as a result, this is a different strategy. You can see that the overall cycle time has been significantly reduced. The overall cycle time would only corresponding to um, 21 hours in this context, okay, while the make span also subsequently reduced, and the make span is also 24 hours. So, you would eventually save time in the case 2. So, time in a production unit is a valuable thing, because everything in the economics eventually would work in terms of time. You have to pay the cost of the labor, you have to utilize the ancillary utilities, everything would be directly dependent on time. Okay. So, and you can see that if you recall in the previous case, when a process is completed, you have to, let us say if it is going to a stage 2, okay, it typically do not happen immediate. It may happen immediate if it is so easy to do so, but otherwise what would happen is you have to actually identify what is called as that. So, there would be some delay in transferring the reactants or products from a one stage to the next stage. So, this would eventually entail taking some amount of time, and you can actually come up with certain transfer policies, and you can choose them depending upon your uh, flexibility and operational convenience and even operational constraint, and you may apply them. So, simplest one, or rather the first one, is what we call as the zero weight transfer. Zero weight transfer is ZW. So, here is eliminate any waiting time. So, your stage 1 to stage 2 is immediate. Zero weight transfer is suitable for process where the product quality, freshness, or is time sensitive. You do not have time to wait. Okay. So, your the seconds, the subsequent process has to be started immediately, and it is time critical. It is typically used in continuous manufacturing, because in continuous manufacturing everything is continuous and typically there is no wait involved. And the second case is, of course, it can also be used in batch if you have the flexibility to do so. The second is no intermediate storage, which typically be represented by means of NIS. No intermediate storage means that the materials or products are transferred directly from one processing to another processing. There is no intermediate storage between. Okay. So, you have your stage 1, your stage A to stage B, between that there is no storage. You are bound to transfer the first stage to the second stage. So, where it would be found in place, okay, application, no intermediate storage can be applied in various industries where waiting times between the processing steps should be minimized, but the process may not require the same level of continuous flow as we found in the zero transfer scenarios. So, now let us look at the last, or rather the third category, where we call it unlimited intermediate storage, which you represented by means of UIS. So, here what is the status here? Okay. So, you have an intermediate storage facility, you in fact you have ample intermediate storage facility within the batch plant to accommodate any materials or products at various stages of the production. So, this is typically used when there are typically employed, rather used, where in the production facilities where there is fluctuating production demands, variable processing times, and and if you need to do any contingency planning. Okay, if there are production unit is typically fluctuating, production demand is fluctuating, you can store them, okay, until things are stabilized. So, okay, so now let us consider the cycle time that includes that by integrating the transfer policies in the previous. So, what we have done initially, we talked about transfer, requirement of transfer, then we learned about the cycle time, okay, then we learned about transfer policies. Now, let us try to integrate, try to marry them between. So, now we are looking for cycle time transfer policies, where you have cycle, how to integrate the transfer policies in a cycle. So, consider a case, uh, consider a case of a 2 product batch plan. Okay, you have product A and product B, and you have 2 stages. In the first stage of A require 4, 6, 4 and 3 hours respectively, and B requires 3, 2 and 2 hours respectively. So, let us look at the zero waiting time. Okay. So, for stage 1, okay, so you look at the, let's start with product A, which is represented by blue. Okay, you have to start, your stage 1 takes 6 hours, stage 2 4 hours, and stage 3 2 hours. So, now your stage 1 of B only takes 3 hours. So, you can start after that. So, you do not have to wait for the entire thing to complete, but you have to make sure that your second stage is available only after 2 hours of operation or 4 hours of operation of stage 2. That is only the bottleneck over here. So, you kind of keep them together. So, you have 2 hours just after. So, you and your third stage is only available after 3 hours of A. So, you can start the, so let us solve this in backwards. This 2 we just keep them as it is. So, if there is no waiting time here, immediately before your stage 2 of B is activated, it is again for 2 hours. If there is no time, since it is 0 waiting time, again you can just move backwards and consider 3 hours of the stage 1 for B. So, this is AB and AB kind of a structure. So, now you can see that in this case, the cycle time would be 6 plus 3 plus 2, which would be like 11 hours. So, now look at a case where you have no intermediate storage. Okay, so which essentially means that where you can, where you can immediately you can no intermediate storage, which essentially means of course you can store in the same place. There is no intermediate storage though. Okay, you follow the production of A as it is. Immediately your stage 1 is completed, stage 2 of the production of B is activated, but you have to we have to keep a watch that your stage 2 of B is only available after 4 hours. So, after 3 hours you have to wait there itself. Okay. So, you are just waiting, but not doing an intermediate storage, and you transfer over here. Okay. Then you can have the 2 hours of stage 2 of B. Okay. By that time, again by that time of the stage 2 of B completed, your stage 3 of A is not completed. So, you have to wait again for an hour, and you transfer them to the stage, you move into the stage 3 of B. So, this is how, so again what you can see over here is the cycle time from here to here is slightly reduced. So, the total cycle time would be just with 6, 3 and 1 hour of wait that you have to do for this particular case. And the third scenario, okay, is about uninterrupted storage. Okay, so what you can do over here, you can start with A is going on 6 4 3, immediately you start uh, uh, stage 2 of B, stage 1 of B. Okay, then what you do, just after the finishing of the stage 1 of B, you store them. So that the stage 1 equipment is freely, and you start with for A. So once the storage time, you will have to storage for you will have to store for 1 hour, because the stage 2 of A is for 4 hours. So you have to wait for 1 hour. Once that 1 hour is completed, you transfer them into the stage 2 equipment. Okay, then you move on. Again, once the stage 2 equipment, stage 2 of the B is completed, still your A processing is not completed. In stage 3, you store them. Okay, you store them and you start moving to, you transfer them to the last stage. So the key difference between here and there is that, so your stage 1 equipment is immediately available in the third case, while the second in the second case your stage 1 equipment is not available. You are not, since there are no intermediate storage, you can only store in the same production vessel. So as a result, you can see 3 cases. Overall cycle time has been reduced from ZW to NIS to UIS. So now so that's what we are summarizing over here. Zero wait time requires longer cycle time. Uninterrupted storage. So UIS, unlimited storage, unlimited intermediate storage requires lowest cycle time. In practical, mixture of all 3 of strategies are used. And cycle time of cycle time of UIS can be computed as the max of n times tau ij, which is summed up over n, and tau ij is the processing time of the product I in stage day, Ni is the number of batch of the product, M is the number of stages, N is the number of products. This is how you could smartly integrate these wait time into the cycle time. So now let us look at the case wherein you can where you consider parallel units. Okay, so parallel units essentially means that you are trying to debottleneck. You also have a parallel unit to work with. So consider a single product production, which has to pass through a fermenter followed by a separator, and the fermenter possibly takes about 12 hours and the separator possibly takes about 3 hours. And you can see the key bottleneck here is the fermenter, because it takes, your separation is completing in 3 hours, but just after that you can't restart. But the problem here is this fermentation takes more time. So the key bottleneck to have the operation in this case is the fermenter. So what you would see with, if there are no parallel operation, you can see the next fermenter is only available after 12 hours. So the cycle time is now 12 hours. So now if you have a parallel operation, what you can see, you can start the fermenter. So this is stage 1. Okay, stage 1 has now 2 parallel tracks. So the immediate the immediate parallel track can operate start operating with the fermentation parallelly. Just after the fermentation is over, it can pass to the stage 2, which is of course a shorter time. So now the total cycle time would be just this, which is the summation of these two, which eventually evaluate to be 6 hours. So the cycle time in this context is typically calculated as tau I by NPJ. So NPJ is the number of parallel unit, M is the number of stages, and so tau I in this case is 12. 12 divided by 2, it would be 6. That's what is coming over here. So alternate option here is, okay. So here also you can use the option of storage. Alternate option is to use an intermediate storage after stage 1, and the amount of material processed at stage 1 should be 4 times to that of the material processed in the stage 2. So what would happen? Again, just to reduce this idle time, okay, you can use them immediately. So you have in storage, so that the production facility is intermediate, is available. So you will not use this wait time. As soon as the product operation of stage 2 is completed, whatever is there, okay, in your storage, you can pass it on to the stage 2, and you can keep on operating what you call without any intermission. So in this case, you can see there is larger intermission, that so eventually result in more cycle time. Here, of course, the cycle time is reduced, but in this case, there is some intermittency. Even that intermittency, or we typically could be able to utilize by means of uh, storing them and using them. For instance, the stage 1, let's say 1200 kilogram. Okay, so you can have a stage 2 of processing for 300 kilograms. So what would happen? Your stage 2 size is also now reduced. You can operate them such that the total amount of 1200 kg which is produced in the previous case can be processed, so that there is no intermittency here. So these, some of these ideas actually helps, as I told, in process design and planning. So so design and planning, typically you can't decouple. Okay, so you should plan, and design also you should have an operational strategy, so that you don't over design and you don't under design. So now let us so see, in every process, that the total horizon time will be that a typical constraint. So total horizon time in a production cycle will be a typical constraint. So let's consider a plant with a one unit stage having m stages for continuous manufacturing of end products, as is the total horizon time in hours, over which one production cycle will be considered. And tau ij is the process time in hours of product I is equal to 1 to n, stage j equal to 1 to m. So major variables which we need to identify or play over is the number of batches that can be produced over that horizon. What is the cycle time? Okay, what is the time allocated from for a product from I to from time horizon h. Okay, and so TLI, of course, we computed as maximum of Tij previously, and theta I, which is the time allocated, would be n times TLI. Okay, total number of time would be number of batches times the cycle time, and we can always understand that this theta would be less than h, which is the total horizon time. Theta would be n TLI. So these are the conditions that you need to satisfy. And if there are n parallel units, tau Li eventually become tau Ij by Nj, as we have seen max of that, as we have seen in the previous case. Okay, so now let us consider design a mixed integer non-linear programming based design of parameters and variables of flow shop plan. Again, single products campaigns, we are only interested in evaluating a single product. So consider, so let's look at the variables. So mixed integer nonlinear programming model is typically used for selecting sizes and numbers of parallel units in batch production, with an objective of minimizing the investment and operating the fixed cost given the production demand. So let's look at the variables. Okay, there are n number of product to be produced. Okay, m number of stages, and tau ij is the processing time of I in j in hours, Sij is the size factor of I in j, which is the total horizon time, Qi is the demand of the product, alpha j and beta is the cost coefficient and cost exponent for unit j, Vjl and Vju are the lower and upper bounds. Okay, and we are interested in identifying the required volume for a unit in the stage j, and what is the size of the product at the end of the m stages. So we can see that what are the conditions. So some cases, so Vj, the required volume should be always greater than or equal to, if it is tightly constrained, Sij times Pi. That's where Sij is the size factor of the product and Bij is the uh, size of the product. So this has to be greater than the total volume that we need to deal with, and Ni would be equal to Qi by Bi, where Qi is the demand of the demand of the product and Bi is the size of the product, and total investment cost. Okay, when assuming the fact that total n would be the number of product produced and alpha and beta are the cost coefficient, we assume that alpha times Vij, volume times volume power exponent, would be like a reasonable model for the total investment cost for m stages. So this is for stage J, and you have such stages. And this is so let's this is how a standard constraint and these are the standard constraint and the cost evaluation. So now let us try to put them slightly formally. The total cost is, as we have seen, sigma over all m n j alpha j v j power b j, and you have the volume constraints, and TLI would be should be greater than Tj by Nj, total time, and horizon. So Qi by, so sigma of Qi by Bi times Li, so of course theta would be less than or equal to the total horizon time, and you have constraints on the volume, and your B and T all should be greater than 0. So see, instead of giving 0 bounds all of this, you can also provide uh, calculate it for k parallel units. So that's what here it is done. So instead of keeping this number exactly at 0, you say that TLI and BI is between a certain lower bound and upper bound, while the lower bound would be the parallel processing and upper bound would be the sequential processing. So this is how these numbers have been obtained. So these numbers we have seen in the previous case. So you have to solve this entire problem to find out uh, optimal size and the number of parallel units. So this particular optimization problem here now, so whatever problem that we have seen graphically, now what we have done, we have done a mathematical formulation of the same, and now if we solve this, so I request you to recall the lessons of optimization that you have learned in your earlier classes. So MINLP problem, when we solve it, so what is that solution? That design aims to minimize the cost, because we wanted to minimize the total investment cost while considering each unit processing times and capacities. Constraints in the model address the volume of processing unit, this of course the volume of processing unit, cycle times and batch sizes, and the total processing time with respect to the planning horizon. And the solution would, as I told, would be yielding to give you the optimal size and the number of parallel unit, of course, which is an integer value, because we are solving a mixed integer nonlinear program. So you can see some of these variables are only belong to I. So I is equal to 1 to n, right? So some of these variables eventually they are all integers in nature. So I'm not going to how to solve it. So you the solution, the details of MINLP, I again request you to recall your lessons that you have learned earlier. And the only point that I need to make over here, this is a non-convex problem, and non-linear because there is a power inside, non-convex because it's an integer constraint problem. So any integer programming problem eventually become a non-convex problem, and is also considering that the cost equation is non-linear. The entire problem is non-linear and convex optimization problem, but the solution of that is giving you the optimal number of signs and parallel units. So now let us consider a concept called slacks. Okay. So what are slacks? So slacks refers to the amount of ideal time between the completion of one task in the start of the one task and the start of the next task in the product cycle. So let's look at a case where a sequence A and B. In the first case, you have stage 1 2 hours, stage 1 5 hours, stage 2 2 hours, stage 3 3 hours. While in this case, stage 1 1 hour, stage 2 5 hours, stage 3 3 hours. So we have learned how to mix them together. So slack typically represent the time buffer that can be incorporated into the schedule to account how uncertainties to prevent overlap between sequential tasks. So now how to keep them together. So see your so the after, so see the stage 1 of B only takes 1 hour, okay, but the stage 2 of A takes again 2 hours to complete. So you have to wait until the stage 1 over. 1 hour for this production, you can only start after 1 hour. So, there is a slack of 1 hour in the stage 1, because the stage 1 of B require 1 hour, but the stage 2 of A is only free after 2 hours. So, here there is a slack, but stage 2 of B we can be immediately started after the stage 2 of A. So, that of course is 5 hours is taking, then eventually that is over, then the stage 3 is 3 hours. So, in this case the slack has become 2 hours. This entire process is 5, and here there is 2 hours. So, sometimes you also need to integrate cleanup times. Okay. So, slack in addition to cleanup times. So, it typically essentially means that, so cleanup time, so you need to clean up the equipment before we start operating. So, let us assume that there is a cleanup time that is coming into the picture. You see that there is no slack in between, because the time for slack has been taken for cleanup. Only in the last case there is some amount of slack, otherwise all the buffer time that we all see here has been utilized for cleaning up the entire process. So, the key thing that you need to keep in mind is that when we formulate the optimization problem, this slack times has to be factored into the total cycle time calculation. So, the goal over here, okay, the goal is to minimize this idle times to slack, so that increase the production efficiency. Ideally, we don't want any equipment to stay idle for long time. Okay. So, since we don't want an idle time, okay, we just keep them active. So, here we see that in this 1 hour, okay, so you start cleaning it, and one more hour you probably take it for clean this. As a result, you have it has been slightly shifted over here, and in between these two, right, when you have so there were 2 hours of slack available in the previous case, okay, and 1 hour of that is again used for cleaning the stage 3. So, then also you have 1 hour slack over here. So, while the other two stages are devoid of any slack times, the last stage has 1 hour slack. So, entire operational process protocol would tend to make sure that there is limited amount of slack variables. And how do you now? So, the next part of the lecture would show how to calculate, how to systematically calculate the slack time. So, we need of course define a start time for the productivity, assuming that the bottleneck occurs at stage 1. So, let us assume that T1 is equal to Ti1 plus Cl Ik1. Okay. This equation defines the start time for the product K in the first stage, taking into consideration the process time Ti for the first stage of the previous product I, and the cleanup time Clki, Cik1 from the previous product. So, it set the initial condition for the scheduling, and for the stage j, okay, so it would be Tj equal to Tj minus 1 and Tj tau Kj minus 1, and how to compute the slack, the calculation of the slack is by which Dj, let us assume, so let us define the slack as Tj, it would be Ti minus, okay, summation of I1 to j Tij, which is of course this, and Clk. So, with respect to the cleaning time. So, this equation calculate the slack time or idle time in each stage based on the total processing time up to that point and the cleanup time from the previous batch. The slack in this context represent the time buffer or delay before the next product that we can start. And how to find the smallest amount of slack? So, you would see that there would be slack that happens in every stage, and when you have such multiple d values computed for various stages of m, so the minimum number of slack would be delta, which is mean of dj, and what we call it as SLK, which is the actual slack. So, actual slack time is the slack time for the transition from the product K to the stage as calculated by subtracting the smallest slack j from the smallest slack delta from each calculated slack. It normalizes the slack times and helps identify the necessary adjustment. So, when you find out the minimum slack time, you kind of subtract it from corresponding Ds to find what is the actual slack time. Okay, so now we talk about, so see what initially what we, so again just to recollect, we talked about cycle time. Okay, we talked about integration of wait times into cycle time. Okay, then we talk about cleanup, then we talk about slacks. Okay, so now we go to the last part of this lecture. Okay, how do you do the scheduling of cyclic process? So initially what we have done was schematically. Now let's use how to use mathematical principles of optimization, which you have learned earlier, to optimize, or rather to finish, or the cyclic scheduling. So we talk about two things after this. We talk about cyclic scheduling, then we talk about something known as state task network scheduling. So, coming to the cyclic scheduling, cyclic scheduling is a process used in manufacturing and production that involves creating a repeatable schedule for the production of different products. So you need to have a schedule that is repetitive, and the process plant people have to just to follow that. It has to be cyclic, so that it in the sense that it should move from start to end. The objective here is to obtain the sequence and timing of the production batches to minimize the total time required for the cycle, which is often involved in considering setup time, processing time, cleanup time, transfer time, everything. Okay, and we have seen how we compute cycle time, and let's now yes, we wanted to compute that, and eventually we would like to optimize that. Okay, so CT is the sum of the processing times and the slack time adjusted by the by an indicator variable. Indicator variable is a binary variable, okay, which typically stands 1 or 0. Okay, and we say that if a batch m followed by a batch m followed by a batch n. Okay, so you say batch L followed by a batch m, you make this indicator variable value to be 1, otherwise 0. This is to make sure that a particular pattern is being followed. Okay, so the total cycle time would be, okay, so which would be tau I plus the slack times that you have to factor in. So the total CT would be summation of IL is equal to 1 to NB tau L1 plus summation double summation L1 to NB M1 to NB SLM SLLM 1 YLM. The equation actually calculates the total time needed for one full cycle of production, including the slack. So you have the cycle time, but now you integrate that the slack time also, because which is something that you need to operationally minimize. So so what you eventually need to do, you need to find a schedule or the sequence in which you need to follow, okay, such that you have to minimize the slack time. So the slack time you computed and you wanted to minimize that, and you have multiple constraints. So the first set of equation, so this is of course all of them would eventually represent an integer programming problem that need to be solved to find the optimal cyclic schedule. The objective is to minimize, the objective what we see over is to minimize the cycle time by determining the sequence of products in batches that result in the least amount of idle time while ensuring each batch is followed exactly another. So you have to follow the fact that every batch is following this particular condition. So okay, so which essentially means that the sequence has been particularly followed. When YLM, the summation of that would be 1, this it typically indicates that particular sequence YLM. So this, and when L is equal to summation of L1 to NB YLM is equal to 1, essentially means that it all again follows a particular pattern. Now, so see what you oversee again. So first two constraints correspond to the assignment constraints, which essentially mean that no batch is followed by and proceeded by not more than one batch. So you can only have one batch at a time, because you have one batch followed by another batch, and so on and so forth. So this particular condition, the summation would indicate the fact that you are not overbooking. So you are so that no batch followed by more than one batch, and the last constraint is the indicate that okay, it is assuming closed cycle. So there when you sum them up, of course this indicator value is more than one, essentially meant that one after other there are schedules over the schedules, and we are interested in solving this problem to find the optimal cyclic sequence. So once that is done, okay, so you can, so another way to approach this problem is by means of geometrically representing something known as state task network. State task network is a graphical representation that captures the state transition and task dependencies in a schematic fashion, which is also called as STN. Okay, in an STN approach, it provides a systematic way to represent a scheduling problem by decomposing it into smaller subproblems, making it easier to solve. So, in state task network, as the name literally indicates, you have various components, states. States represent the different state that a production unit or equipment can be in different manufacturing process. It could be ideal, processing certain equipment, product, cleaning, maintenance, and so on and so forth. This can be the state of any equipment, and the task. So, task essentially means that something what is being done or what operation is being performed in a particular unit. The task can be, it could be mixing, heating, cooling, reaction happening, material transfer, cleanup, and so on and so forth. And the dependency. So, state task network capture the dependency between state and task. Certain tasks can only be performed when specific states are achieved, or certain states can only be reached when specific tasks are completed. So, these dependencies are crucial in sequencing the scheduling operation. For instance, once the product is, you can only clean up a vessel once the product is being made and transferred. Got it. So the dependency, so you cannot invoke a cleaning process in between a production process. You have to wait until the production is completed, then you invoke the cleaning process. So, this dependency is always there. So, this dependency also have to be taken into consideration, and there would be resource constraints, of course. For instance, equipment availability, raw material availability, and of course, if there are labor involved, there would be a personnel availability, and so on and so forth. So, by representing the scheduling problem using state chart network, research and practitioner can apply various scheduling algorithms and optimization techniques to efficiently allocate resources, sequence tasks, and minimize the production time. Like as in, we solve this problem by cyclic scheduling to identify the minimum cycle time that minimize the cyclic sequence. We also now use a slightly different. So, we try to use a graphical representation and translate that into a mathematical problem and find out how the uh, states and tasks can be assigned. So, look at a simple case. Okay, so here you have a product A. So, a raw material A is getting heated, splitted into two. Okay, it is going to a reaction unit 1, reaction unit 2, and reaction, then post that going to so after the reaction product. So, once the point is splitted, it is B. When the reaction is completed, the top line has D and C, and you have separation to separate E and F. So, just to explain the schematic, this state task network represents a state how the raw material A in this case is used for producing product E and product F. So, this is a product F and this is a product C, okay, with E is another byproduct. So, it is a 3-step process involving heating. Okay, at this moment you will have to heat the material, and then you have to keep for 2 hours for the intermediate reaction, and followed by separations. So, it is 3 hours. While in this case, okay, you have to have then intermediate. So when you have the intermediate D, you have separate, and you will get F being the product and E being the byproduct. So in this case, the state task network represents as a recipe in terms of transfer and material. Different state task network may be need to be considered if they are processing in a different process speed. So there is in a state task network. So you can see there is a state and a task, but there are no other information. So the equipment will not be represented in state task network because their assignment to task is treated as unknown. At the moment, you really know what equipment you use it, and your optimizer is interested to give them that solution. So jacketed reactors can be used for performing task 1 and 2, 1, 2, even 1, 2 and 4, while separation can be separated by means of typically by means of separation columns and so on and so forth. So storage is typically represented as accumulation of material. So now how to solve this problem in a state task network optimization formulation. So look at the case. So we have task T, each task has a processing time P, which is assigned to different equipment J and capable of performing that task. Then you have state S. Okay, it could be different material, intermediates or product. They are connected through so they are connected to SAS through material flows, and you have multiple batches, and you would the size of the batches is BJI, which vary and represented by the flow of material and time. So scheduling horizon would be discretized to certain intervals H, allowing precise timing and task, and we have multiple constraints. So first constraint is what we call it as equipment assignment constraint, which ensure that each equipment can only perform one task. You can't double. At the moment, only one equipment would be inactive and they will do its job. And you have capacity constraints in terms of storage, and you have mass balance constraints and utility constraints. So this is where you have to connect the learning that you have done in your earlier part of this lecture, where you talked about flow sheet and material balance. So those balances that we have learned here is coming here as constraints. So in this way you try to relate between the contents of the earlier part and the at the moment, just to make the greater picture and to appreciate the connection. And what is objective? So objective function is to is about always about profit. If you have to maximize the profit function J, which is of course a function of sales, purchases, inventory cost and utility cost over the scheduling horizon. And mathematically, this problem is formulated as a mixed integer linear programming problem because include both continuous variables like batch information and binary variables, for instance, task assignments, equipment assignments. So let's assume that we have discretized time like T, which is available over a horizon H. This defines the discrete time horizon, discrete interval, which allows the scheduling to be broken down to manageable periods of time. And the objective function here is to maximize the net profit, which is a sum of sales minus the sum of purchases of final inventory value and the utility cost. Okay, so utility cost has to be taken out. Okay, uh, the sum of the sales minus sum of the purchases, final inventory value, and of course the utility cost. Sales, purchases, okay, inventory value and the utility. So some of the terms which are positive, some of the types are negative. Okay, utility consumption, utility is a consumption. So you got it. Sales purchase is a cost, and the other two are summed up. You can see the variable. Okay, so whatever CDT, CST, D, CSTR, CSH, CUT, they are suitable cost coefficient of each operation. DST and DRT as the sales and purchases of state, UUT is the demand of utility, SST is the amount of material stored. So, this is something that we need to, this is the cost, overall cost that we incur by means of performing an operation in state task network, which we would like to ideally minimize. Then you have various constraints, okay. Of course, first of all is an assignment constraint, okay. So, Wij should be always lesser than 1. So, when it will become 1 when a unit starts and processing at a task I at the beginning of the period T. So, equipment unit J can be assigned to at most 1 task at 1 period. This prevent, as I told previously, overbooking. So, the next is sequence. So, W sigma of Wij is equal to sigma of Wij at T plus P is equal to sigma of Wij T. So, this essentially means that once a task is started, the same equipment continues to work for the required processing time without switching to another task. You can't break an operation. So, heating is done. So, heating is continuously done until the entire operation is completed. Or if it is cooling, if it is reaction, you can't break uh, the process in between, and you can't have the batch sizes exceed the overall capacity. This is a batch, this is the overall capacity, Vij is the maximum capacity, and material storage has to be, do not exclude the storage capacity, and we have the material balance, okay. So, the mass balance and material balance in here. So, which is this particular equation actually speaks about the mass and material balance. So, mass balance equation ensure that the material flow is always conserved for a state S and time. The amount of material from the previous state, previous time plus any produced or purchased or transferred is equal to the something that is utilized, stored or transferred out. So, this is how this left hand side and this right hand side is getting balanced. And yes, we will have also bounds on the amounts produced and purchased must be equal to the hold up plus the amount of consumed and the sale. So, DST should not be greater than D small DST, and RST should be less than or equal to small RST, where DST and capital RST are the minimum and maximum demand for the state at the beginning of the period T. So, it should not violate the demand constraints. So, if you solve this entire problem, you will get the sequence in which the sequence and assignment of the equipment is in your state task network over here. So, the sequence and the task that you need to get attempted to, and this would help you to create the state task network, which is of course an equivalent form of scheduling, equivalent form of Gantt chart. So, this is another way to represent the entire operational schedule. Okay. So, one thing, one additional constraint that we need to have over here is the constraint on the utility. You have to have the total utility cost is equal to the, so if alpha and beta are the coefficient associated to the utility, and it is also connected to W, the operational cost, and the batch volume cost. So, you have the total cost of utility, and this is how you compute the total utility, and it has to be minimum. You cannot have utility used forever, and eventually it should not affect, it should not be overused. It's a major contributor in your cost. So, you should have a upper cap for how much ever utility you can use. So, again, just to summarize, you have the objective function, okay, which is all about the cost. You have assignment constraint that takes care that overbooking, and also another constraint that helps you to for continuous processing without breakage of a particular process, and bounds on capacity, batch sizes, material storage, material balance constraint, okay, and bounds on total amounts produced plus purchased, and also on the utility. And you will, so these are the all constraints, everything written in context as a linear function. So, this is an MILP formulation that aims to optimize the industrial process by determining the best scheduling for tasks based on economic factors such as sales, purchases, inventory and utilities, while considering time discretization for manageable planning. Various constraints are introduced to ensure feasibility of the schedule, including equipment assignment, overlap, capacity limitations, batch size, material storage, and utility consumption with available limits. The formulation includes, of course, mass balance, maintain the material flow equilibrium, ensuring the input and output of materials across the states and the time periods are accounted for, thus adhering to the production requirement as and demand. So, the material balance formulation that you have learned in the earlier part of the course, this is how we tied up to the design in an optimization framework in summary. So, just a few more side topics. So, when we do scheduling, it typically can be reactive or preventive. Okay, reactive when you deal with an unexpected events. So even if you plan something, there can be an unexpected event that can happen in the plan. Okay, so it is of you need to deal with this unexpected events while in process. So, for instance, there is a key equipment can break down, then in this case, so when you typically act if there is an unexpected event happen. So, reactive scheduling is all about that, which is quickly rearranging the tasks and resources to minimize the impact on the production schedule. The ability to respond promptly and effectively into this disruption schedule is maintained, and again maintaining the product quality, meeting the customer demands, and minimizing the financial losses is the key. So, it is react. So, if your scheduling is reactive, suddenly you can reconfigure and find out the optimal solution. We say that the schedule is robust. The same applies to preventive. Preventive is more about proactively preventing the disruption. You really need to know there is a predictable mechanism that helps you to find out there is an upcoming disruption, okay, which you could just now plan and act, thereby helping contingency planning. Okay, so maintenance regular maintenance schedule, so that when that can happen, so that you can just integrate them, and also contingency planning would help. And eventually, this is all typically done means of what is going to by kind of envisaging what is going to happen, what are the potential risks, and what are the issues that can happen, and integrating them into the schedule to mitigate their impact if such a scenario, if at all occurred. And preventive scheduling eventually contributes to reliability and eventually reduces the unplanned downtime and thereby enhancing safety. So, this was a slightly long lecture, but let us summarize what we have learned. So, we learned about cycle time, okay, cycle time reduction, and we found that there are 3 strategies to integrate uh, wait times, and each of them would have a different sequence of cycle time effect on the cycle time reduction strategies for, and we also looked at cycle time reduction strategies for in a multi-product batch plants. This include parallel unit transfer policies, scheduling a process plan, focus on optimizing the sequence and timing batch operation to maximize the production efficiency, minimize downtime. This involves a careful balance between operational flexibility and the constraints of the production environment, aiming to achieve high utilization rate and minimizing batch cycle time. So, where you talk about operability, etc., would here is where they are trying to join and shake their hands together. Cyclic scheduling is typically used for processes with regular repeating pattern, while and we also talked about cyclic scheduling, and we also talked about state task network, wherein scheduling is used to for more complex process that require detailed representation and may include a mix of batch and continuous operations. And we concluded the lecture content by talking about what is reactive scheduling, which is responding to the disruption, and preventive scheduling, which is anticipating and mitigating potential disruptions. Okay. With this, we kind of conclude our optimization based design, and we would slowly shift gears from upcoming classes to sustainability and sustainable principles of sustainability and sustainable systems design, how that can be integrated in computationally in the process design. And thank you for patiently listening. See you soon. Bye.